Thanks for watching. And if you find PDEs hard and confusing, this video is for you because I want to show you that sometimes the formulas become super concrete and simplified. So here, let's solve the heat equation UT is duxx with initial condition E of minus x. Now, the nice thing is we do have a formula for the solution, which is simply given by U of xt, which is the multiplication of F with what's called the heat kernel, but here multiplication is convolution. So F star G of xt, and here you will see in a second, it's nice to use the following definition of convolution. F of x minus y, g of yt dy. And all this boils down to, we need to use a definition of g, which has a 1 over square root of 4 pi dt, and an integral from minus infinity to infinity of e of minus x minus y, and an e of minus y squared over 4 dt dy. So here we just pulled the 1 over square root of 4 pi dt out. And all we need to do is simplify this a little bit. And here really all I did, I rewrote the formula but expanded this out because the nice thing is now this e of minus x doesn't depend on y. So this comes out and we're left with e of minus x over square root of 4 pi dt. And then the integral of this exponential function, so e of y minus y squared over 4 dt dy. And here's the idea, we will focus now on this exponent, because what we'll do, we will complete the square, and then once we complete the square, we will be able to turn this into a Gaussian, which will eliminate a lot of those nasty terms. So let's do that. So step 2. So now let's focus on, so y minus y squared over 4 dt. So we can factor out this minus 1 over 4 dt. And then we're left with y squared minus 4 dty. And remember how to complete the square. So we need to subtract half of that. So that becomes minus 1 over 4 dt. So y minus 2 dt squared. So half of that. And then you subtract the square of that. So minus 2 dt squared. And the nice thing is there is a simplification, because if you now expand this out, you get minus y minus 2 dt squared over 4 dt, and then minus minus becomes plus, so 4d squared t squared over 4 dt, which already you see lots of terms cancel out. This 4 cancels out, the d cancels out, oh no, not the d, and then the t's cancel out. And again, in view of writing this as a Gaussian, let's put everything under that square. So y minus 2 dt over square root of 4 dt squared, and then plus dt. Very good. So once again, that was the exponent in our Gaussian. So now we need to go back to original integral. So step 3, if I'm not mistaken. So u of xt, so remember there was this e of minus x over square root of 4 pi dt. And now integral from minus infinity to infinity with our new and improved exponent. So e of minus y minus 2 dt over square root of 4 dt squared, and then just e of dt. dt and then dy. Which is already very nice. This dt just comes out and can be pulled here, and we end up getting the following formula. So after we pull this e of dt out, we're left with this exponential function, this really nasty term, and this almost Gaussian integral. And to turn this into the Gaussian integral, we just need to use a u sub. So I believe that's step 4. So unfortunately, we're already using u for our solution. So let's use p, like pi m. So p is y minus 2 dt over square root of 4 dt. So then dp, that's with respect to y. So 1 over square root of 4 dt dy. And so dy is square root of 4 dt dp. And moreover, what happens to the endpoints? So p of minus infinity, it's minus infinity minus 2 dt over square root of 4 dt, which is minus infinity. But the cool thing is, the same thing is true for plus infinity. So p of plus infinity, it's plus infinity minus that, which is still plus infinity. In other words, the order of integration is still the same. And so in the end, after the dust has settled, we end up getting uxt is e of dt minus x over that nasty term, so 4 pi dt, integral over still the same points, e of minus p squared, and then square root of 4 dt dp. And the cool thing is, you already see that a lot of terms cancel. This 4 cancels with this d cancels with this, and this t cancels with this. Which is exactly what we wanted, because we were worried about that nasty t on the denominator. And so what we're left with is e of dt minus x over square root of pi, and an integral from minus infinity to infinity of e of minus p squared dp. And here's a beautiful thing. So this thing, all it is the Gaussian integral, which I've computed in 15 different videos, by the way, and we find that the answer here is square root of pi, which, as nature would like it, cancels out so elegantly with this square root of pi, so that in the end, we get a very, very simple exponential function. And you see, the math powers to be want us to be happy because we started with the PDE ut equals duxx with initial condition e of minus x. We had some very nasty formulas, and we ultimately found that u of xt is actually very easy. It's e of dt minus x. In fact, it's so easy, we can even plug in to check if this works. So this is kind of optional. But if you calculate ut by the chain rule, a d comes out. de dt minus x. And then duxx, that becomes d. And then you differentiate this with respect to x. So you have a minus and minus. So minus 1 and minus 1, e of dt minus x, which gives you the same thing. And last but not least, if you're curious, what about the initial condition? What's e of 0 minus x, which is e of minus x. So in fact, only green flags and everything checks out. Alright, I hope you like this heat equation extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.